All right. So as I said, this is what we have done. The common emitter amplifier summarized in one slide. All the relevant equations that you see here, equations associated with DC analysis, equations associated with the small signal analysis, with gain, input, output resistance, lower cutoff frequency, upper cutoff frequency, and voltage swing. As I said in the beginning of the course, that there are other specifications of common emitter amplifier also, other specifications of amplifiers also besides the ones that you see here. We have noise, we have power dissipation, we have other kinds of power supply rejection ratios. There are several others, but these are amongst the most important ones that are there. So as you can see here, what I wanted was, so far we have done analysis mostly, and in this particular discussion, we want to take a look at the common emitter amplifier from a design perspective. And so the first thing, as you can see from this particular chart here, you want gain, you want all these things that are there, and all these specifications, all these characteristics of amplifiers, they depend on a handful of parameters. Handful of parameters, for example, you see AV depends on ICQ, Rn also depends on ICQ, V0 also depends on ICQ, and then cutoff frequencies also depend on ICQ. So almost all the parameters that you see there, except for the output resistance, everything depends on ICQ. So when you are trying to adjust ICQ to obtain a certain value of AV, the value of ICQ, which is optimum for obtaining a certain value of AV, may not be optimum for obtaining the value of Rn, or may not be optimum for obtaining the value of V0M. So what you invariably end up with is that you find that there is a trade-off. If you want gain to be high, you'll have to compromise the input resistance. Or if you want voltage swing to be high, again, you may have to compromise the gain. So a part of design process is to be aware of what are the trade-offs. So as a designer, what are the trade-offs that you can make in this particular amplifier here? So let's look at that. Some of the trade-offs we've already seen. For example, a trade-off between voltage gain, input resistance, and output resistance we've already seen. Expression for gain is here. Rn is R pi parallel RB, R naught is RC, and we saw these three graphs. That if you try to increase input resistance, the gain will fall, and which is apparent from here. Rn is primarily dependent on R pi, and so if you increase Rn, you'll have to increase R pi, which means you'll have to decrease current, and a decrease in current will result in fall in the gain here. So this is what you see here. AV versus Rn trade-off. Similarly, you see Rn versus R0. If you leave gain unchanged and you try to get a lower output resistance here, then you'll have to get lower input resistance as well. So because gain is constant, so the only way you'll get lower output resistance, which means lower RC, then you'll have to, because gain is constant, lower RC means you'll have to increase ICQ. And if you increase ICQ, the Rn will fall. Okay, so you see that particular trade-off between Rn and R0. And then you see AV and R0 trade-off, that if you keep input resistance constant, then if you try to increase the gain, the output resistance will also increase. Or if you try to get a smaller value of output resistance, then you'll have to sacrifice the gain also. And we said that from these equations, we can manipulate these equations and combine them together in this particular form. I'd earlier given you a simplified version where we, instead of AV, we had AV0. And so right now we have the full gain taking RL into account. So if you combine them up, this is the expression that you get. And it's easy to see that these terms, this term here and this term here, both are larger than 1. So this is what we have been saying, that AV Rn by R0 will always be less than or equal to beta. There can be situations where you obtain exactly equal to beta. For example, let's say if RL is simply not there, all right, and there are circuits where we don't have RB. If you recall that we had a way of biasing from the emitter side using dual power supplies where we didn't have RB. Okay, so in that case, this factor would be 1. And if you don't have a load, which is rare, you will have some kind of a load. So AV by Rn by R0 can be, what we are saying is, in rare cases can become exactly beta, but most of the time will be a little less than beta, depending on these factors that are there. Okay, so this sort of summarizes the trade-off that you can see here. It's not so much as how much lower than beta this particular factor is. The point is that this factor on the right is relatively constant. Okay, R0 by RL, these are relatively small values here. So the right-hand side, you take it as a relatively constant term. So what it is telling you is the trade-off between AV, Rn, and R0. It tells you how one can be exchanged for the other. So this is something that we have seen earlier. Now, apart from the trade-off that you see here, trade-off between, for example, gain and input resistance that you can carry out by varying the value of ICQ. So that's one trade-off. There's another way of carrying out trade-off between AV and Rn, which is what we had seen earlier, that if you have this amplifier, and these are AV and Rn for this, what you can do is you can leave a part of emitter resistance unbypassed here, and what happens is that the gain gets reduced by a factor 1 plus GMRE1, and input resistance gets multiplied by a factor 1 plus GMRE1, if RB is sufficiently large here. So this is another way of carrying out the trade-off between the gain and the input resistance here. If you're not happy with the gain that you see here, not happy with the input resistance that you see here, right? And then you can get a higher input resistance by having a little bit of emitter resistance, which is here, unbypassed. So it will increase your input resistance, but at the expense of the gain here. So you can't avoid that. The gain, and if you're leaving the output resistance unchanged, you can't do, at least in this amplifier, you can't avoid the exchange. Increase in gain or decrease in gain are accompanied by simultaneous changes in R. Okay. As an example, you can see these two amplifiers here. So we have an amplifier here. Notice this particular part. Gain is 110.7. Rn is 0.82K. And then you notice that we have left 50 ohms unbypassed here. Simply taken same design, same biasing, everything is the same. If you note all the resistors, everything is the same. All that we have done is 0.56K. We have broken it down into 510 ohms, which is bypassed, and 50 ohms, which is unbypassed. And then what do you obtain? See, you sacrifice gain from 110 to 18.2. You sacrifice gain, but look at the input resistance here. So you've managed to increase the input resistance from 0.82K to 2.76K. So that's another mechanism by which you can carry out trade-off between the gain and the input resistance by having this part of the resistor which is unbypassed. Okay. Now note that by ICQ and other things were kept all unchanged. Okay. The previous case of gain resistance trade-off was using ICQ by altering the value of ICQ. This one is without altering the value of ICQ. All right. Before we leave, I've already mentioned this, that while we are talking about gain, input, and output resistance, the usual view is that the common emitter amplifier, since we are summarizing the common emitter amplifier as well, the usual view is, and if you look at this particular design, you get a fairly large gain and a value of input and output resistance in a kilo ohm range is considered as a moderate value. So the usual view is that the common emitter amplifier provides you with a high gain, medium or moderate values of input and output resistance. But we had already also seen that I can take this common emitter amplifier, redesign it. It's up to us. So we have already seen that output and input resistance can be exchanged. So I can make input resistance high, but then I'll also make output resistance high. So these are also possibilities which are there here. So don't look upon common emitter amplifier as simply high and medium and medium. You can see here, you can get all values which are high as well. You could also get all values which are low as well. Low gain, low input resistance, low output resistance. You can also get that. So this is a better summary of what the capabilities of common emitter amplifier are in terms of gain, input resistance, and output resistance. Rather than talking about high, medium, low, and all that, this is a better summary of the capabilities of the common emitter amplifier here. What is it that you can get here? AV, Rn, and RC. All right. There is a gain and swing trade-off. So we've seen now gain, input, and output resistance trade-off. There's a gain and swing trade-off, output swing here. So here is an expression for gain. AV is ICQ, RC parallel RL here. And we have seen that the swing is a minimum of these two terms, VCQ minus VCSAT, and the term over here. Now, what we can do is, if I look at this expression for gain, ICQ RC parallel RL is over here. So I can take this and substitute it over here. So we get here V0M is minimum of VCQ minus VCSAT and this one here. Well, if we look at it, it may appear, well, why is there a trade-off? I can get high gain and therefore high V0M. Right? If you look at this expression, if I increase the gain AV, then V0M also increases. So why am I saying there is a trade-off? Where is the trade-off here? High gain, you increase the gain, and therefore V0M also increases. Then, you're right. So the trade-off, you're right, comes in because we have a fixed VCC. When you have a fixed VCC, so that's the point. Let's say I take V0M equal to 0.5. Suppose voltage swing is 0.5. Then we know from the first term, VCQ has to be greater than 0.7. And then we know that ICQ RC must be less than VCC minus 0.7 minus VE. Kirchhoff's law from VCC to ground. Right? So we see that ICQ RC is less than VCC minus 0.7 minus VE for a swing of 0.5 volt. All right. Let's say I do the same analysis for a swing of 3 volt. VCQ must be greater than 3.2 according to this equation. ICQ RC must be less than VCC minus 3.2 minus VE. So if you look at these two, ICQ RC obviously here is larger than ICQ RC over here. It's larger. And the gain is depending on ICQ RC. So what this is telling you is, if you try to increase the swing here from 0.5 to 3, ICQ RC is dropping. Okay. But a more interesting way of seeing the gain swing trade-off is through this. The swing that you get from a common emitter amplifier is usually very poor because of large harmonic distortion here. So if you look at these two amplifiers here, look at the behavior of these two amplifiers here. You get AV of 110 and swing of 0.39 volt at a harmonic distortion of 1.9%. Okay, large gain, but a fairly poor swing with this much harmonic distortion, 1.9%. And we said, again, what you can do is you can leave a part of emitter resistance unbypassed here. So what you do is you've sacrificed gain to 18.2, obtain much better linearity and much lower harmonic distortion, and look what you have obtained. 2 volt swing with a harmonic distortion of 1.8%. So for the comparable harmonic distortion, 1.9 and 1.8 here, you have increased the voltage swing by a large factor here, but at the expense of the gain. So again, you see that there's a gain swing trade-off. You can obtain greater linearity, greater swing, lesser distortion, all of that through this particular means. Okay. So if you're really, the other point that I want to say is, if you're really looking for a good swing, if swing is your interest, this is not a suitable stage. Common emitter amplifier, simple common emitter amplifier is not a good stage here, as you can see from these numbers that you see here. But look at these numbers here. So common emitter amplifier with emitter degeneration resistance here. Another way of, another terminology, term for this particular amplifier is an emitter degeneration resistance here, or with a emitter unbypassed resistor here. When you put that, then you are able to get much better swing. Okay. So if you're really looking for a swing, go for this particular stage. This is not really suitable. Okay. All right. So again, as I said, you can see a gain swing trade-off here. All right. If you're simultaneously trying to get 110 gain and 2 volt swing, that would be difficult. Because of these fundamental trade-offs that are there. Let's look at the other one, gain bandwidth trade-off. Very popular gain bandwidth trade-off. So bandwidth is the mid-frequency range. So on one side you have the lower cutoff frequency, on the other side you have the upper cutoff frequency, right? So bandwidth is decided by these two ranges here. So look at, we said the bandwidth, lower cutoff frequency is predominantly defined by CE. This particular time constant or the frequency associated with this particular one is what usually decides my cutoff frequency here. And we had an expression for omega L, which is 1 over CE. And the effective resistance CE was RE parallel, RS parallel RB plus R pi by beta, the resistance seen into the emitter here. Now, trade-off is in order to illustrate the trade-off, what we have taken is that this term, let's say my amplifier is being driven by a low resistance source here, RS is small. So if RS is small, RS parallel RB becomes small here, so I'm neglecting it. And so we are left with R pi by beta. And R pi by beta, you know, is again a very small quantity. R pi, let's say it's a resistor, 1 kilo ohm, gets divided by beta of 100. And therefore you are left with a value of 10 ohms here. Versus RE, typical values of RE are much larger in kilo ohms range here. Okay, so R pi by beta is much smaller than RE typically. So you can neglect RE as well. And so what you are left with is omega L approximately equal to beta. Beta goes up by CE into R pi. All right, so this is a simplified, in order to illustrate the trade-off that is there, beta by CE into R pi. Rn, we have said, is R pi parallel RB. And in a design, many times we may keep RB much larger than R pi. So let's write Rn as simply R pi here. So let's combine these two together, omega L and Rn here. And we get omega L into Rn is beta by CE. All right, omega L multiplied by Rn is beta by CE. Now, what we are saying is the following. Beta is a constant for a amplifier, so this is fine. And we are saying there's an upper limit to how large a CE you will use, because the larger capacitors that you use become bulky, and you know, you don't want to use 1,000 microfarad and all that. So it's a huge capacitor. You don't want to do that. So there's an upper limit on CE. Whatever that upper limit is for you, keep that there. So the right hand side is then a constant, depending on how large a CE you can potentially use. So the right hand side is a constant, beta by CE is a constant, and therefore, is there a trade-off between lower cutoff frequency and input resistance? If you want a lower value of lower cutoff frequency, what will you get? A higher value of input resistance. So that's fine, right? Both these quantities you want. You want a higher input resistance and you want a lower value of omega L. So there's no trade-off between omega L and Rn. You can get lower value here and you'll get higher value here, which is good. But we also know that AV Rn by R0 is approximately equal to less than or equal to beta. So we can combine these two together. And if we combine them together, we get AV by R0 into omega L less than or equal to CE. So now we see that if you're not changing your input and output resistances, let's say you're keeping them constant, then if you try to increase AV, then you'll have to increase omega L also. So the two are related together. If I don't change my input and output resistances, if they are fixed, and if you increase the gain, you'll have to increase the lower cutoff frequency. So you'll have to exchange one with respect to the other. On the other hand, if you can vary R0, then you can avoid this exchange here. Then you increase AV0 and you increase R0. Then omega L may remain constant here. Okay? But if R0 is a constant, it's telling you that there is a trade-off between gain and lower cutoff frequency. You'll have to exchange one with respect to the other here. Okay? So that's the trade-off which can potentially be there depending on what you can keep constant and what you cannot. Okay? So that's the gain bandwidth, gain lower cutoff frequency trade-off. Let's look at the upper cutoff here. Omega H. 1 over Rs dash parallel R pi. This is all the input time constant, Rc dash C mu. Okay. Let's do some simplification. To see the trade-off, we'll have to simplify a little bit here. So let me call this quantity R pi by R pi plus RBB here. C pi is GM tau F. GM is ICQ by VT here. Gain is, remember we discussed in the last lecture that gain is a little bit lower than GM RC dash because of the drop across RBB. So that's this particular term. And then what we can do is we can take with these terms here, we can rewrite this particular expression in terms of the gain. In terms of the gain, magnitude of the gain here. All right, so basically we have taken GM here and GM RC dash here and written in terms of the gain. So what you see is omega H and all these things that you see over here. What this is telling you is again, there are, as we saw in the last lecture, there are ways of changing the gain. If you change the gain by changing ICQ, by changing beta, if you try to increase the gain by increasing GM, which will require an increase in ICQ, then what will happen is that an increase in GM also results in increase in C pi. And therefore, an increase in gain results in fall in omega h here. Okay, so that's the trade-off that this particular expression is describing. Increase in gain will come at the expense of lower upper cutoff frequency if you try to do it through the route of ICQ. The other one is, which is not really apparent here. So you'll say, well, I'm not going to change my ICQ. I'll not try to increase the gain by increasing ICQ, but I'll try and increase the gain by increasing RC. Okay, I'll try to increase the gain by increasing RC. If you do that, if you increase RC, yes, this particular term increases, but we said the contribution of this term is not that large. Okay, contribution of this particular term is not very large here. So if you increase RC, your gain will increase, and omega h may not change that much, except that please keep in mind that the effect of RC is not simply here and here that you see here. If I increase RC, well, this term is actually becoming smaller. But effect of RC would also be there on C mu, the value of C mu that is there here. Why? Because as you increase RC, note that for a fixed VCC, what would happen is as you increase RC and we are not changing ICQ, so what will happen is that the collector voltage will change. The voltage here at this particular node will change. And the base voltage is, we are not changing anything else, base voltage is fixed. So collector base voltage is going to change. And as collector base voltage changes, please recall when you calculate the value of C mu is collector base capacitance. So that depends on the collector base bias. So as you change your RC, as you try to increase RC, the collector bias, this voltage here decreases, and that will cause a change in C mu as well. So you have to look at that aspect also. And as this value changes here, omega h will also change. All right. But you know, changing RC and increasing gain through that, again, you could do that. But that also comes at the expense of a higher output resistance here. So if you're not going to touch the output resistance, leave it as it is. Then if you try to increase the gain, the only route to increase the gain is ICQ, and you'll end up causing a decrease in omega h. All right, so that's the other trade-off. So for example, in this case, we kept the RC constant here, and for a particular design, we varied the gain, and you can see how the upper cutoff frequency, how it changes as you try and increase the gain here. So that's another important trade-off, which is the upper cutoff frequency versus the gain that you see here. All right, so what we have then is, how many trade-offs have we seen? Trade-off between gain, input and output resistance. That's one particular trade-off. Trade-off between gain and swing. That's the other one. And then the trade-off between gain and bandwidth. That's the other trade-off that is there. Okay. All right. Let's look at, so having seen this trade-off perspective, let's look at the design of common emitter amplifier. I'm not going to carry out design, but let's see what does it involve. So design always begins with a set of specifications. So specifications could be gain is greater than 100 plus minus 20%, which means that you'll have to give me a gain between 80 and 120. It should not vary beyond those limits. At t equal to 300, R naught is 2.2K, let's say. Rn is 0.75K, VOM, whatever. Swing with some harmonic distortion. Lower cutoff frequency, upper cutoff frequency. And some constraints will be given to you. RL is 2.2K, RS is 50 ohms. Sometimes a constraint may be given that supply voltage has to be exactly 9 volt or less than 9 volt. Or sometimes there may be no constraint on VCC. You're free to choose. Even if nobody is saying it, it's understood that your design should be low cost, low power. Even if whoever you are designing the amplifier for, it's understood that you should do these things that are there here. All right, so a set of specifications are given, and to satisfy these specs, now you may ask, where do these specs come from? Who is going to give these specs? Well, there are, what I would say, the specs will come from a customer, but there are two kinds of customers, very broadly. There is one customer who this may be a standalone amplifier. This may be a standalone amplifier, which means that it's a final product. Okay? And so depending on, the person where he's going to use for what application, audio amplifier, video amplifier, or whatever it is. So based on that, we derive these specs here. The other kind of customer is not really a a physical person or a company which is asking you to do that. What happens is you're doing a multi-stage amplifier design. And when you're doing a multi-stage amplifier design, where there are, let's say, 3 or 4 stages that are there. So 3, 4 stages are there. And so you have an overall specs for a 4-stage amplifier. Okay, for a 4-stage amplifier, you have an overall specs. Now, and this is a part of that 4-stage amplifier here. So what happens is, from that overall specifications of that 4-stage amplifier, you derive the specification for this particular stage here. So your customer may be your boss. He says he has already done the top level design of the 4-stage amplifier and has said stage 1 should be like this, and stage 1 should be like that, and stage 3 and stage 4. So specs are coming from a higher block which may be a 4-stage amplifier. So specs are coming from that design of a 4-stage amplifier. From there you are getting these particular specs. Where are the specs for a 4-stage amplifier coming from? Well, they may be coming from the specs of an ADC. Your whole 4-stage amplifier may be a part of analog to digital converter. So from an analog digital converter, you look at the block diagram and you look at the specs of A to D, and from there you find out that you need a certain specs for an amplifier. And from the specs of the amplifier, then you derive this should be the specs of my stage here. So it's coming from there. Now, where is the specs for A to D converter coming from? Well, maybe A to D converter is part of a blood pressure meter. Right? So A to D converter is a part of blood pressure meter. So you look at this whole system level design of a blood pressure meter. From there you derive what are the specs of the A to D, and from there you derive what are the specs of the big amplifier, 4-stage amplifier, and from there you derive eventually what should be the spec of this particular stage. All right? So blood pressure meter may have a specs there, but eventually you'll have to derive from there what should my small stage, what should be the specs of my small stage. Okay? So it could be a standalone amplifier, or it could be a small part of a blood pressure meter. Okay, so depending on then the overall system design, you derive these particular specs here. Okay, so let's say, so right now this is arbitrary, a set of specs which is given here. Now what are the, so you have to meet these specs, and typically in a real design, you don't have a schematic. You remember we have many schematics available here. This is a common emitter amplifier. We've seen that, well, we could leave a part of emitter unbypassed. That's another schematic. Or we could use a dual power supply. Dual power supply here. There are other ways of designing. So nobody is going to really tell you meet these specs using this particular schematic. So the first task is to find what would be a right schematic. What would be a right schematic, topology or schematic which will satisfy these specs here. So here we have simplified the task for you in the sense we said, well, let's try this. Let's satisfy these specs with this schematic here. So then what are the resources at your disposal? Resources in the sense that design variables are all the resistors, R1, R2, RC, RE, all the capacitors, CB, CC, CE, VCC, if nothing is specified on VCC, well, you have a choice of VCC, and the transistor. There are hundreds and thousands of transistors that are available. You have to choose a suitable transistor. So, in the sense that now you have to carry out this particular design to meet these specs, and finally you'll have to determine these variables here. R1, R2, all the resistors, all the capacitors, supply voltage, and transistor. And what is the knowledge base on which you are sitting? All the equations that you see here. Right? This is your knowledge base. All the analysis that we have done, these are all the equations that are there here. And so this is what we have to do. We have to take these specs, We have to take our knowledge base here and arrive at these values here. All right. So, and also you have to be aware of what is available. Transistors. For example, also you have to be aware of all the values of resistors that are available. You know that resistor 2.2 may be available as a single resistor. 2.3 is not available, right? As a single resistor, you'll have to connect 2.2 plus something, and that makes the circuit a little bit, bigger here. All right, so this is what you have to do. So here, so how do we go about doing it? So so what you have to do is, you can see here, using this knowledge that you have, these equations that you have to map, map these two here. You have to find out these values here in a systematic manner to satisfy these specs here. Now, what I want to point out is, instead of going to these specs here and directly trying to find out what is R1, R2, RC, RE, if we look at the amplifier equations, it makes more sense if I look at my amplifier equations to proceed in a different manner here. If I look at the amplifier itself, we find a lot of amplifier characteristics, AV, RN, V0M, FL, FH, they all depend on the bias point. So rather than saying I have to determine R1, R2, RC, RE, what I would say is, from the given specs, what you have to determine is a suitable bias point. What is a suitable ICQ? What is a suitable VCEQ? And I've added one more thing. What is a suitable emitter bias here? The voltage drop across the emitter. We'll see in a minute here. So looking at these specs and the equations that you have at hand, you have to determine a suitable bias point. Then you have to, as part of that, you'll have to determine a suitable value of RC, a suitable value of CE, the critical ones I'm pointing out, suitable value of CE, and you have to choose a transistor based on what? The choice of your transistor would be guided by what kind of beta are you looking for. There are transistors with beta of 100, there are transistors with beta of 200, maybe 250. So it would be guided by what kind of a beta are you looking for. What kind of remember the upper cutoff frequency depends critically on the transit time, tau f, and the capacitances. So what kind of capacitances, what kind of, how fast a transistor do you really want? Okay, so those are two major considerations in this case, which will decide what kind of a transistor do you want. If you don't choose a proper transistor, tau f may be too large, the capacitances may be too large, and you may find that you can't satisfy the FH that is there here. Or you may unnecessarily choose a very expensive, very fast transistor with very low value of TF and very low values of capacitors, but they're unnecessary for the specs that are given here. So you have to make a choice of transistor based on transistors have many characteristics, but I've just hinted to you at least four characteristics. One is beta, the other one is the parameters associated with the frequency response of the transistor, tau f, CG0, and this one here. Now, what I said is, so if you want to proceed with design, look at the specs, look at your equations, and try to arrive at these values here: ICQ, VCEQ, and VE. RC is relatively straightforward. RC is you choose according to R0. Okay, if you have a R0 of 2.2K, less than that, you'll choose RC less than 2.2K. So that choice is relatively simple here. And once you choose this, then you'll find the choice of CE will also become easier. You have one single equation for lower cutoff frequency, and all these choices have already been made. So choice of CE will not be difficult here. One single equation, one variable, and that would be fine here. So one of the critical things in an amplifier design is the bias point. What bias point should I choose? What ICQ, what VCEQ, and what VE? How do I choose that? That's very critical here. Okay. So in that context, ICQ and VCEQ we can obviously see. We can see it in our equations that are there here, where ICQ comes in expression of AV and RN and all that. That's not too hard here to choose ICQ and VCQ proper values here. So let me spend a little bit of time. This is not something which is talked about. The choice of VE. Okay. So choice of VE means what is the drop across this emitter resistance? How do I choose that? Should I choose the drop across the emitter resistance 1 volt, 2 volt, 3 volt? How do I choose that? So the drop across this particular value across RE, that choice has a lot to do with the stability of your bias point. Okay. So for example, this is ICQ, and if I take its derivative, this ratio here, change in collector current over change in beta, we can write it as 1 over beta RE plus RB, and let's define this as. So it's easy to show the following. VE, the drop across the emitter resistance, is ICQ times RE. And I can divide it by VT, multiply by VT, divided by beta, multiply by beta, and rearrange this particular term into this one here. All right? Rearrange this particular term in this particular manner here. Further, noting that this RE by RB by beta comes over here as well, I can rewrite this is in this particular form. VE is XB. Note what XB is. RB by R pi. S stability, inverse of stability minus 1 multiplied by VT. So it says that the choice of the emitter bias point is decided by two factors. One is how much stability are you looking for? What value of S? That is one. And the other one is how large a ratio of RB over R pi do you really want? And recall, why do we want a large value of RB by R pi? Because that decides my input resistance. Input resistance is RB parallel R pi. So you want RB to be larger than R pi. How large do you want to keep? And these two things will decide what your emitter bias point is. So you have to make two choices. Stability. Normally an application will not, in our case, our design, said, you can see here stability. It says plus minus 20%. The gain should remain between 120 and 80. So that will give you an idea. From there you can derive what kind of an S do I want. I'll show you another result here. What kind of an S do I want? And from there, from the stability issue, I'll get this value here. And this choice, RB by R pi, will give me XB. And that will decide the emitter bias. And we've already seen what decides VCEQ, what decides all of that from gain, from gain and swing and all that. We've already seen how those things are decided here. Another way of rederiving this is, so for example, if I take stability of 0.1, VE turns out to be XB into 0.23. If you choose XB, RB by R pi equal to 10, then 10 into 0.23, so you find emitter bias should be 2.3 volt. On the other hand, if stability you want very, very stable 0.01, then VE turns out to be XB into 2.3. And if you take RB by R pi still as 10, this comes out to be 23 volt, which is out of question. You can't do it. But you may get this kind of stability 0.01 if then you compromise here. You make RB equal to R pi. You decide to do that. RB equal to R pi, and then XB is 1, and V equal to 2.3, which you may still manage. So you get a very, very stable amplifier. S is equal to 0.01, very stable against beta and other things, but you'll have to make RB equal to R pi. All right, so that may have consequences with respect to input resistance here. Same thing, instead of S, what we can do is, this is what we had in the exam. We were not given S, we were said, well, the percentage change in collector current was given as 5%. So let's say if Y is IC2 minus IC1 by IC1. What is IC2 and IC1? IC1 is the current that you get for beta 1, and IC2 is the current that you get for beta 2. And so the change in current is denoted as Y, and then that can be expressed in terms of this parameter again, beta RE by RB. Or what you can do is, you can get this parameter X, beta RE by RB. You can get this parameter in terms of how much change in collector current due to beta you can tolerate here. So if you're given Y as, if you're given, let's say beta 1 is 100, beta 2 is 200, the percentage change in current that I can tolerate is 5%, 0.005. You find you can derive from here the value of X, which is 10.52, which tells us that VE should be 0.27 times XB here. So XB, still we have to make a choice, XB being RB by R pi. All right, so from those considerations, either from if you're given beta 2 and beta 1, and from there you find out how much change you can tolerate, you can find out what is the value of VE. So again, to summarize, VE is determined by the choice here, by these two choices here, stability and this choice here, RB by R pi. Now, typically what happens is, when you are faced with a lot of equations and a lot of specs, the design becomes a bit difficult in the sense that where do I start? How do I find the right values here? And so what people tend to do is, when confronted with complexity and you can't handle it, then what do? Well, people have in those cases based on, sometimes those are right, based on experience. You have rules of thumb, which says choose the emitter. So I showed you here a precise way of selecting the emitter bias point. How do you choose an emitter bias point? Okay, on what basis do you choose? But if you don't want to, if somebody doesn't go through all of that, then what one may have is a rule of thumb in the sense, well, let's choose V equal to 1 volt. 1 volt would be okay, or 2 volt, arbitrary. So what I want to show you is next is, so when confronted with, okay, before that, so let's look at this. The other important point is, very, very important point is supply voltage budgeting. What do I mean by that? Supply voltage is a scarce resource. It's a scarce resource, and therefore you have to budget it, depending on how you allocate. So let's see if that makes sense here. Where is the supply voltage dropped here? VCC. See, leave aside R1 and R2. That's just for biasing here. The important point is VCC is dropped across this RC, is dropped across VCEQ, and is dropped across the emitter resistance. 3 places VCC is dropped. And you have to allocate how much of VCC is allocated to the drop here, how much is allocated to the drop here, and how much is allocated to the drop here. All right. What does this drop control? This drop is ICQ times RC. What does it control? You can easily see here. ICQ times RC controls AV. ICQ times RC may also control VOM. So the drop across RC is deciding your gain and swing. Okay? So what I can do is, I can take these two equations and I can write it in this form. ICQ RC parallel RL is AVVT, or ICQ RC parallel RL is greater than this. So your swing and gain are going to decide this drop. If you require a gain of, let's say, for the moment, let's ignore this for a moment. Let's say you require a gain of 100. Gain of 100 with a certain RL and all that will demand a certain value of ICQ RC drop. You'll have to allocate that much drop ICQ RC to realize that much gain. Look at this one here. VCEQ we know is decided in terms of swing. My swing has to be greater than this particular value, or has to be less than this value here. So VCQ has to be greater than or equal to VOM plus VC sat. So this drop, how do you choose this drop? Based on the swing that you're looking for. This drop has to be at least larger than this particular value. What about this drop? We just saw. This drop is depending on how much stability you want. Stability and how much is that ratio, that RB by R pi that you want here. So look at now, when I say supply voltage budgeting, let's say you have a 9 volt supply. The design says that you have to make your amplifier run on 9 volt. All right, so you have 9 volt available. Now you have to decide out of that 9 volt, should I give 3, 3, 3 here? Arbitrarily just give 3, 3, 3. Does that make sense? 9 volt is there. Allocate equally. Equality. 1/3, 1/3, 1/3. Does it make sense? It doesn't make sense, right? You should allocate depending on what your demands are, right? How much AV you want, how much swing you want, and how much stability you get. So you'll decide. Based on the demands of your specifications, you'll decide how much to allocate here and here and here. Can you also see that somebody, let's say, tells you that design a particular amplifier, like I've given you here, like the specs that I gave you, and I put a constraint that VCC has to be 9 volt. VCC has to be less than or equal to 9 volt. In fact, by going through this, the specs that I gave you, you will see that with 9 volt supply, you just don't have enough supply to allocate to this, and this. 9 volt will not be enough. So I've given you a set of specs which are unrealizable, which can't be realized, because 9 volt supply is simply not enough. I don't have enough drop here for gain, I don't have enough drop here for swing, and I don't have enough drop here for stability. I don't have that. So then your task is to go back and tell, well, these specs are unrealizable. Give me at least, not 9 volt, give me at least 12 volt. If you give me 12 volt, then I can do the design. But 9 volt, I can't do the design. All right. So this is very, very important, because it's telling you what decides the value of VCC. Is the gain and the gain part here, is the swing part here, and is the stability part here. And you can look at this particular equation, which is summarizing all these 3 parts here. in terms of gain and swing here, and in terms of stability. You have to have these quantities in order to arrive at here. Now, this is the point that I wanted to bring. So as an example, so we take this equation, and as an example, let's say somebody says, give me a gain of 200 and RL by R0 is 1. In the sense that RL is, let's say, 1K, and we choose output resistance also equal to 1K, so this is 1. If I plug it here, the first term itself comes out to be 10.4. And then I will need something for the swing, I'll need something for the stability. Obviously, my VCC is going to be 12, 15, something like that. Or somebody says S has to be 0.01. Well, then the last term itself, 0.01, if I choose XB as 10, RB by R pi, this itself is 23.4. All right, so this equation is telling you about VCC. What decides VCC? Is the gain, is the swing, and the stability, and the choice that you make about RB by R pi. So you can see, without looking at that, we would have been tempted to take RB by R pi to be large, 10, 20, 30. But you can see what price you have to pay. If you take RB by R pi to be large, look at what happens here. So for a design like this, as I said, choose RB by R pi equal to 1. And then you may still get 2.34, which is practical here. So let me wrap this up by pointing out that, as I said, when faced with design, so I'll come back to Cedra and Smith. So when faced with design, very often we resort to rules of thumb here. So if you can read all of this, it will take you 2-3 minutes to read. So the book is talking about the trade-offs that are there. You know, for a given value of supply voltage, the higher we use VBB, the lower will be the sum of voltages. Talking about this budgeting, supply voltage budgeting. On the other hand, we want to be large in order to obtain high gain and large swing. The issues that I just talked about. Thus, now read this. Thus, as is the case in any design, we have a set of conflicting requirements, and the solution must be a trade-off. True. As a rule of thumb, one designs for VBB about 1/3, 1/3, 1/3. All right. I mean, rules of thumbs are right. When design becomes complex, everything you can't derive from the equation. You derive things from experience. You know that things have been done in the past and they work fine. So you do derive from experience. But this is a too small or too simple a problem where you apply rules of thumb. You have, as I showed you, you have equations which allow you to choose. How do you choose VCE based on the swing? How do you choose the drop across ICRC? You don't simply choose the ICRC drop as 1/3 VCC. That's arbitrary. That's arbitrary. Depending on the gain, you choose how much drop to keep, 1/3 or 1/4 or 2 volt or 3 volt and all that here. So this is a too simple a problem where you start applying these arbitrary rules of thumb. In this case, we have relevant equations which allow you to decide how to obtain this particular drop, and this particular drop. Okay.